Hello everyone and welcome to another video. We are going to be talking about the Schrödinger equation today, a very important equation in the field of quantum mechanics. So having established the basics of quantum mechanics in some of our past videos and the particle wave duality of electrons, photons, and other atomic elements, we can begin to dive into modeling their behavior, and this is where we get into the Schrödinger equation. Now, the Schrödinger equation is used to determine the energy of a quantum system. Then, by applying specific conditions, we can use this equation for a multitude of systems. Now, we can actually derive the Schrödinger equation from basic physics. We start with a basic wave function, psi equals a sine 2 pi times x over the wavelength minus t over the time period, t being time, x being position. Now, a wave function is going to describe the amplitude of a wave and how it depends on the variable's position and time. For our convenience, only sinusoidal waves of wavelength lambda and period t are considered, where t equals 1 over the frequency. A is going to be the peak amplitude of our wave. Now, plotting this wave function gives the following graphs. This first graph shows the amplitude as a function of time at a fixed position. As you can see, we see this clear sine wave going on as time advances. And down here is going to show amplitude as a function of position at a fixed time. As you can see, as we move along this sort of x position in the positive direction, we again get this nice sinusoidal wave. Now we can take this basic wave function and clean it up. We can condense our variables by replacing 2 pi lambda with, like this, with a simple wave vector k, and we can replace 2 pi over t, like this, with the angular frequency omega right here. So if we plug these two into this equation, we then get a new wave function that looks like this. So apologize for the handwriting. Psi of x of t equals a sine of the wave vector times position minus omega times the time, just like that. And this is going to be our basic wave function that we are going to use to later derive the Schrödinger equation. Now, a Schrödinger equation is going to involve a special kind of a wave called a standing wave. Basically, two waves are going to interfere with one another, one going in the forward direction, like this, and one going backwards. And when they interact, we get this sort of interference right here where we can see some constructive interference where the two waves overlap, and then some sort of nullified interference where we get these fixed nodes that are spatially fixed. And we can kind of see what this looks like in motion right here. We see how we have these fixed nodes, and the wave is sort of oscillating back and forth, just like this. Now consider two waves of the same frequency and amplitude moving in opposite directions. The resultant wave is going to be the sum of the individual amplitudes of those two waves. So we can write this as the psi of x of t equals a times sine of the wave moving in the forward direction and the wave moving in the backward direction. We can just write that right here. And notice how everything is going to be the same except this time portion of each equation. We are going to flip the sign of this to signify that the wave is moving backwards in our backwards wave. So then applying a nice trigonomic identity, that being sine of alpha plus or minus beta is going to equal sine of alpha, times sine of beta plus or minus cosine alpha times sine beta. Applying that to these two equations up here is going to give us a sort of standing wave equation, that being down here. Psi of x of t equals 2a sine the wave vector times x, cosine times of omega times t, and we can simplify this as just the psi in relation to x times the time-dependent nature of our wave function, cosine omega t. So we have our wave function for a standing wave, but why is this relevant? Standing waves are going to play a key role in quantum mechanics as they represent stationary states where the measurable properties of a system do not change with time. we can take advantage of the wave function where we take the second derivative of the wave function with respect to x and set that equal to 1 over velocity squared times the second derivative with respect to time, something like this right here. So by substituting our wave function into this wave equation right here, we are able to derive the Schrodinger equation. So first of all, by substituting that in, we get on the left-hand side that the second derivative of the wave function with respect to x is going to equal cosine omega t times the second derivative of the wave function just with x over dx squared. And then on the right-hand side, if we plug this in, 1 over v squared times the second derivative of x of t over t squared, we are going to get negative omega squared over v squared times the wave function just with respect to x times cosine omega t. And then by setting these two equal to each other, as in this we do in this equation up here, we are able to get cosine omega t times the second derivative like this over dx squared. We get this equal to negative omega squared over v squared, the wave function times cosine omega t. We get our cosine omega t's to cancel out. And then if we actually rearrange this so that's all equal to 0, we get the second derivative with respect to x like that, plus omega squared over v squared times the wave function with respect to x equals 0. So we get like this. And then by using some of our identities we discussed previously, we can use angular frequency equals 2 pi times nu, our frequency, plug that in right here. And then for our velocity, we can use the equation v equals lambda times nu, just like that. And by substituting all that in, we get a newer equation, the wave function with respect to x over dx squared plus 4 pi squared nu squared over lambda squared times nu squared. These two cancel out. We can use our de Broglie relation. Lambda equals h over p and get a new relation. Again, the second derivative of the wave function with respect to x plus, let's see, what is this going to be? It's going to be 4 pi squared p squared over h squared using our relation h bar equals h over 2 pi. We can use this right here. And then for our momentum factor, we are able to actually get a new relation by considering the total energy is a kinetic energy plus the potential energy, which can be simply written as the momentum squared over 2m plus the potential energy. Rearrange this, we get p squared equals 2m of E plus the potential energy. Plug this in right here, and again gives us the second derivative of the wave function with respect to x plus 2m of E, oops, let's rewrite that, E minus v of x over our h bar squared times the wave function like that equals 0. And then just by rearranging all of this, we are able to get the time-independent Schrodinger equation right here. Negative h bar squared over 2m times the second derivative of the wave function with respect to x plus the potential energy times the wave function equals the total energy times the wave function, just like that. Now this looks pretty complicated, but it's actually very simple to analyze. It's basically the kinetic energy plus our potential energy equals the total energy. The kinetic energy is going to be this right here. Our potential energy is going to be this term right here. And of course, our total energy is this right here. And by applying the specific conditions of a system, we can determine the possible wave functions right here of that system. Now, if the time dependence of our wave function matters, we can just adjust this equation a little bit. It stays the same on the left-hand side. We have our kinetic energy plus our potential energy, but instead of our total energy, we have this term right here. I times h bar times the partial derivative of the wave function with respect to t. Now, we will not be deriving this equation, but this is useful when, the time dependence of a wave function matters. Now, that is the Schrodinger equation and the background to how we obtain it. Hopefully, this was a helpful explanation to connect this abstract quantum mechanical concept to topics in physics you might be more familiar with. I know it's a lot of derivation. Reviewing the textbook is very helpful. But anyways, thank you all so much for watching, and I hope you have a great day.